Okay, hello once again. Thank you for being here today. This is the third installment of the Lungs on Fire speaker series. Our work takes place on the traditional, ancestral, and unceded territories of the Musqueam, Squamish, and Tsleil-Waututh people, and we pay our respects to them in the spirit of truth and reconciliation. Now, as many of you know, the Lungs on Fire project is a 5-year team initiative funded by the Canadian Institutes for Health Research and led by Dr. Chris Carlston of Legacy for Airway Health and the UBC Division of Respiratory Medicine. Now, this speaker series is part of the Lungs on Fire Knowledge Mobilization Initiative. And really the aim is to generate conversation about how can we optimize health guidance to reduce the harms from wildfire smoke. And wildfire smoke, of course, is the focus of the Lungs on Fire project. But developing health guidance is not actually an easy task. There are a lot of different considerations, both scientific and ethical. So I'm Stephanie Harvard, and as the co-chair of the Knowledge Mobilization Working Group for the Lungs on Fire project, I have the pleasure of welcoming the speakers that we've reached out to be part of this speaker series. And today I have the pleasure of introducing Dr. Angela Yao. Thank you so much for being with us today, Dr. Yao. For those of you that are perhaps not familiar yet, Dr. Yao is a senior scientist at the Environmental Health Services Unit at the BC Centre for Disease Control, and there she leads the Climate Preparedness and Adaptation Program. Her research focuses on the population health impacts of climate change, including hazards such as wildfire smoke, extreme temperature that of course can co-occur, and other important weather events. Today, she will address the topic that was selected, one of the several topics selected by our KM working group, which is air quality data, forecasts, and alerts, effectiveness for reducing harms from wildfire smoke and other considerations. We always add the other considerations in there because what we want to do with this series is generate conversation, and we're wanting to ask scientists like Dr. Yao to present the considerations that are relevant from your perspective. Now, if you've attended one of these events before, you'll know that what we do is we invite speakers to present for up to an hour, 45 minutes up to an hour, and then we host a discussion and a Q&A for up to 30 minutes. So if everything that comes to mind for you is accomplished in less than 30 minutes, we will, of course, end early. But we do invite you to think specifically about how does what Dr. Yao covers today affect your thinking around how wildfire smoke guidance should be designed. So with that, I'd like to hand it over to you, Angela, and thanks again for being here.
Thank you so much, Stephanie. Let me share my screen. Great. Hello, everyone. Thank you so much for having me here to talk about this topic. I would consider myself a heavy user of air quality data, forecasts, and alerts, and I'm mostly using it in the public health protection side or aspect. So very happy to be here and just share some of my experience as I've worked with these data. And I think I would describe my presentation as a semi-structural presentation. I try to kind of give a structural overview of my thinking about these data or warning. But I also have some parts that are really non-structural, just some kind of thoughts and things that I want to share and spark some discussion if people are interested in joining the discussion. So that's what we'll have. And I'm sure I don't need to spend too much time on explaining the importance of air quality and its impact on public health in this group. I think most of you are quite familiar with all the potential health impacts from air pollution and wildfire smoke in particular. So I just want to briefly talk about, why air quality information is so important for protecting public health from these pollutions or from wildfire smoke, and from three aspects that it can enable research and surveillance, it can raise public awareness about this problem, and it can inform our actions. First, these air quality data is essential for doing any type of research or surveillance about the public health impacts. A prime example is the development of the Canadian Optimized Statistical Smoke Exposure Model. That's led by Naman, Paul, and others in our group. And I'll actually talk a bit more in detail about this model later in the presentation, but I just want to put it here as an example that since the development of this model, it has enabled so many different types of research. And here are just some published examples of studies that range from looking at the synergistic effects of wildfire smoke and hot weather, looking at the cost effectiveness of air quality filters, air filters for asthma complication management, and also looking at long-term impacts of wildfire smoke. And these are just published studies, and I know there are a lot more ongoing studies that are using this data, and probably only possible because these data exist. And it's the same for surveillance. And the right-hand side, you see an example of climate change and health data application that we developed in our group, which include an indicator that uses data from CanAwesome to indicate areas that had the number of days in different areas that were impacted by wildfire smoke. And then the air quality data can raise public awareness about this problem. The one examples that I was most familiar with is how the reporting of air quality from the U.S. Embassy in different parts of the world enable the air quality improvement in many parts of the world. So example is the embassy in Beijing, once it started to tweet out the air quality data from the embassy, it really created a movement that focused on improving air quality in Beijing and in China in general. So it was certainly disappointing to see that the U.S. Embassy stopped doing that this year, and given the benefit of these worldwide air monitors and the value of the data that they provided and the public health benefits globally. And next is to inform actions. So we know air quality can have profound impacts on our health, and we should take actions to mitigate these health impacts. And air quality information is needed as the foundation to inform these actions. Almost every country or region has its own air quality index. They may have different algorithms or different thresholds, or looking at different types of pollutants. But they're all aimed to provide guidance to the public so that they can take actions accordingly to protect health. Here are just some examples: the US AQI, the Europe AQI, and also what we have in Canada, the AQHI. And we'll talk about this in more detail later in the presentation. And when I think about air quality data or air quality information, I usually think about them in 5 dimensions, or describe them in five main dimensions. That's the spatial coverage and resolution, the temporal coverage and resolution, and also the accuracy or precision of these data. And when we talk about spatial coverage, I would say that from the perspective of wildfire smoke, spatial coverage is very important. Here, this map, what you're looking at is the number of days between 2010 to 2022 with high biomass smoke exposures, and mostly wildfire smoke. The data from Can Awesome. And the reddish, the more red color indicates more days impacted by wildfire smoke. But the minimum is 10 days on this map if it has any color on it. So you can see that in Canada, very large areas have been impacted by wildfire smoke. And the areas that are more or most impacted are also areas that tend to be more remote or more rural area, which is quite different from some conventional air pollution like traffic or industrial emissions. So that really makes spatial coverage of data information very critical when we try to see whether it is useful for wildfire smoke or not, whether they can cover these areas that are most impacted is very critical. And then when we think about spatial resolution of a source of data, it depends on how variable this type of air pollution is. And for wildfire smoke, it happens to be it can be very localized. It really depends. Sometimes it's regional impacts, and a lot of times it's regional impacts, but also sometimes it can be very localized. And this figures kind of depict some of those localized impacts. You can see the smoke kind of follows the valley around Mount Baker. And as you can see, these things, the smoke dispersion depends on factors like topography, distance from the fire, whether an area is upwind or downwind of the fire, or there's some local meteorology that can change its concentration as well. So the spatial resolution of the air quality data will decide whether it can capture these localized impacts, and depending on the purpose or focus area, and really kind of decide how useful it is as well. And for temporal coverage, we know that a data source, it can have historical data, it can have real-time current data, and it can also have forecasting data that can look into the future. And we know historical data is very important for research, to look at the relationship and also to study the health effects, and also for establishing the baseline for surveillance. So we need to know what was happening to kind of try to derive a proper way of surveillance. However, real-time data and forecasting is also very essential, and is essential for informing actions. A few years ago, when I was doing a PhD, I did a study to look at the relationship between hourly PM 2.5 exposure and ambulance dispatch during wildfire seasons. And on this left-hand side, the figure shows some of the results, which what it means is that the effect from wildfire smoke related PM 2.5 on ambulance dispatches were largest at like 0 hours. So what that means is that at the impact or the effect is really quite immediate. So once you get exposed, you start to see these effects. So that makes forecasting really important for informing action, because we do want this kind of ahead of time notice or ahead of time planning in order for us to avoid, to try to reduce our exposure as much as possible. And these information is also very important for things like event planning. As you can see, if you need to decide whether we're continuing with an event or whether we need to do any arrangement of a large event like the Grand Fondue that just happened this summer, and happened to have wildfire smoke impacts, you do want information ahead of time so that you can make the best arrangement for your event participants. And a temporal resolution about the air quality information is, how frequent it gets updated, right? And the wildfire smoke, it can change hour by hour, depending on, the meteorology. And there's also usually some diurnal patterns in both the fire behavior and the smoke emission, as well as the meteorology that can affect the transport and dispersion of smoke, like whether there's an inversion or other weather patterns. And here, this figure shows an example of the hourly PM 2.5 over 2 days. So as you can see, it's like if we look at the daily average, we can just see a peak of a peak in the daily average. But within that daily average, they actually still quite variability hourly within that 2-day period. So high temporal resolution is also a very useful feature of a source of air quality data with regard to wildfire smoke. And it is actually it is important for informing people. So when is a better time to go out for a walk, or take your kids to the playground? That's really some of the questions that we often get when our area is impacted by wildfire smoke. And this is especially important when a community has been impacted by wildfire smoke for a prolonged period of time, because this information really is important for them to live their life while trying to reduce their exposure as much as possible. So they really need to find a better time. Maybe it's not, as good as before when there's no wildfire smoke, but it is still better to know, when is a relatively good time to go out for a walk, to maintain, to maintain a routine, a daily routine. That's very important for people's both physical and mental health. And a somewhat related topic is the temporal rest of is what the averaging time that we're talking about for a specific measurement. This question is especially important when we try to compare a measurement with a certain guideline or standard. I actually recently reviewed a manuscript where the authors were trying to advocate that we should align AQHI, which is based on hourly or 3-hour average measures. So they're advocating it to be aligned with the WHO PM 2.5 guideline that you see here, or which is either a 24-hour average or an annual average. And so this alignment would not really make much sense because they have different averaging time period alone. The averaging time selection for it can be different for different pollutants, and it can it is also relevant to what type of health outcomes that we're interested in. So are we talking about the acute outcomes, or are we talking about the long-term outcomes? And then you might require different averaging time as well. And finally, we would want to talk about air quality information, about their accuracy and precision. So accuracy means that we want the data to reflect the true air pollutant concentrations in the air. And precision, or I would consider it as like consistency, is that even though it may not be measuring or reporting the exact same the actual true air pollutant concentrations, but it present the same value at the same pollutant level all the time. So that's kind of the persistent or the precise or consistent aspects of that measurement. And which also means that if there's any type of bias from the true value, we want that bias to be systematic. So it's always higher than the true value, or it is always lower than the true value. But we don't want them to be, all over the place. It can be higher or lower, at different times. So that's the least that we want that measurement to be. So ideally, you would want the data to be both accurate and precise, especially if you need to compare that concentration with a set threshold that might have any legal or operational implications. You want that to be really accurate and precise. But for some purposes, maybe we can, loosen a little bit on the requirement for accuracy, and maybe some very relatively precise measurement is still useful. For example, when we look at wildfire smoke forecast that we will talk a bit more about later in the presentation, we may want to pay more attention to whether it has the smoke plume, whether the smoke plume is forecasted to come our way, instead of focusing on the exact value of PM 2.5 that it is forecasting, because there can be a lot more uncertainty there. But the general trend, or I would consider it as categorical impacts, would still be if useful for our purpose in planning our actions. That's similar for some of the low-cost sensors that I will talk about later, that we also want to, it may not be 100% accurate, but we also still want it to be, precise enough that we can trust the trend it's reflecting. So talking about the 5 dimensions, I would like to talk a bit about the different types of air quality information with that 5 dimensions in mind. Um, the first that we're most familiar with is definitely the regulatory air quality monitors. Um, these monitors, so far they are the most accurate information that we can get about air quality. These instruments in these monitors are usually they must meet some kind of standards, and they also have standard operating procedures for how to maintain or calibrate them. Right now in BC, there are approximately 100, over 100 continuous air quality monitoring stations. Metro Vancouver operates approximately 20 of them, and the rest of the 80 managed by the province and by the Ministry of Environment and Parks, and also the industry themselves. So, like if you get permitted for industrial site, there you need to set up some air quality monitors that's for monitoring purposes. There's this standard procedure, and there's quite frequent technician visits and audits to make sure the accuracy of these monitors. And there's also, a team of data validation to make sure that the data is validated. So that's also what makes these monitors very expensive to establish and maintain. That's also why there's limited spatial coverage of these monitors as well, because we just cannot afford to have them all in all regions or all places. But these information is really essential, important for all the other tools or data source that I will be talking about. It is it is used for ground truthing almost all the other tools that we have today. And one of them is called low-cost air sensors. So because it is challenging to have these regulatory grade monitors in more places, there's these so-called low-cost air sensors came into the picture. I remember when I started grad school 15 years ago, these sensors were mostly still in the research environment. But now, as I think recent years, there's really rapid development and really they really get into the consumer market and get more and more kind of use and validation from different organizations and the public as well. And yeah, so as you can see, when we add in low-cost sensors to this map, it is it's definitely a much denser network than the ones that we had before, just with the regulatory monitoring stations. So these low-cost sensors, they are relatively less expensive. But the costs range from a few hundreds to thousands, depending on what type of pollutants are measured or what kind of technology it is using. So it's it is called low cost, but I think it is low cost comparative to a regulatory air monitor. So it can still be costly in our in our sense of the cost to the general public. And it is usually easier to install because it's the target market is the public, and it usually comes with instruction on how to install them, and it's usually more straightforward than the ones in regulatory monitors. And The accuracy and precision varies by brands, by technology, by installation, how it's installed, where you place it. So there's a bit more uncertainty in there. Um, but there are all, right now, I think there are a lot more studies to look at the accuracy and precision and how to improve them as well. One common problem or common issue with these low cost sensors, especially those that's used technology or instrument called nephenometer, is the impact of humidity on the measurements. So it's usually when the humidity is high or different than what it's supposed to operate in, it would create some kind of artifact on the data. And that's why if you look at some of the data reported on the website I show here, the AQ map, the data from low cost sensor is actually corrected with a correction factor that consider relative humidity. So that's one area that we're trying to improve the usefulness of these data. And one distinct benefit of low cost sensor is its ability to be used both indoor and outdoor. That's quite important because it really fills a gap of indoor air quality measurement or air quality information. All of the regulatory data monitors their all outdoor measurements, and many of the other tools that we talk about are also focused on outdoor air pollution levels. So the use of these low cost sensors that can be placed both indoor outdoor it provides the opportunity to do studies like this. This is a study that's led by Dr. Eric Coker from our group, that they use these indoor outdoor data to develop a machine learning model that can actually try to predict indoor PM2.5 levels with outdoor levels and in combination with some neighborhood characteristics data. And indeed, what they found in this study is that when you look at the relationship between indoor PM2.5 and health outcomes, it's the effect size is actually larger. So that's sort of a very rare information that we can get because there's just not very much indoor air quality information that's available. And the next type of air pollution or air quality data is satellite images. Satellite images have been used to derive air quality information for a couple of decades right now. And previously, we primarily accessed these data from the US NASA. But recent years, we also see quite a rapid development and expansion of information available from its European counterpart called Copernicus. So, these are, they're usually publicly available data that's retrieved from satellite images. One of the widely used measurements used for air quality from these satellite images is called aerosol optical depth. It measures the extinction of a ray of light as it passes through the atmosphere. So the more particles in the area, the higher the more the more extinction it will create. And so it's the AOD, or aerosol optical depth, will increase. And the different satellites and different instruments would have different spatial and temporal resolution. So, for example, AOD measured by MODIS on Terra and Aqua, these two satellites, they usually has daily global coverage at spatial resolution around 1 to 5 kilometer. Some other satellites may have higher or lower, resolutions. And there's usually a trade-off between spatial and temporal resolution from a particular instrument or satellite. So for example, if you want higher rate spatial resolution, you need to zoom closer to the Earth, which makes your window of view smaller, so that it would take more days, so more days to pass through the same location on the Earth. So that's sort of like you can't have both, but there's a bit of a trade-off there. One distinct characteristics about satellite images is its bird's eye view. So it's looking at the Earth from above. This gives it good spatial coverage of the Earth because it just looks, high, top, up there. But it also leads to some limitations that, for example, it measures aerosols or pollutants in the total column of the atmosphere, not just the ground level. But we're mostly, from the public health perspective, we're mostly concerned about the surface level exposure that people can actually be exposed. But the satellite images, it measures the whole total column of the atmosphere that it's not easy to distinguish whether it is aloft or whether it is on the ground. You also will not be able to have measurements when there is cloud coverage. Also, if you use images that's we call visible band, so it's that means like just photos, or when you want photos, when you look at photos, you need light. So there's no measurements at night. When there's no light, and you can't really use the visible band to measure to have that image. Next one is models. Models are powerful tools for sure, and because they can have very high spatial and temporal resolution. It has good spatial coverage as long as you have, the input data ready for that area. Then you don't really need actual air pollutant measurements in every point of your prediction model. And it usually many of these models can have the ability to forecast into the future. And the only kind of like concerns or people's worry is it's the accuracy, how certain or uncertain we are about the model performance. And one type of these models is called physical or deterministic models. These models, they're based on all we know about the physical or chemical processes of fire and air pollutants. And we set up all the parameters to simulate how the fire or the smoke would progress under different scenarios. For example, we can do experiments in the lab to generate data on how much PM 2.5 would be emitted from burning different types of vegetations under different conditions. And then you derive these called emission factors that can be incorporated in parts of these models to then we would simulate, okay, what is burning, and then we can calculate, how much smoke that would come from that burning using these emission factors. And sometimes assumptions would be needed if there's no real data available, so that you can complete the whole kind of physical and chemical process of the whole kind of from fire to smoke to dispersion, the whole process there. On the screen here, you see the two major wildfire smoke physical models in Canada. On the left is the Environment and Climate Change Canada fire work model. And on the right is the blue sky smoke model that's developed and maintained by a group at UBC. I would use the firework model as an example to kind of go over, as an example to describe how, on a high level, how these models work. So in fireworks, they take in information about fire activities from satellite images. So so they know where the fires are. And then they also take in meteorological output, so things like weather forecasts from the GEM model. And then they put in these information into a field consumption spatial information system where they can calculate based on these information as well as the field type and field conditions. So what type of vegetations and things like that, to calculate for each hotspot how much smoke is emitting from there. And then from these daily emission estimates, they use another system to calculate or distribute it as an hourly exposure. And then all of these input into the GEM-MAC model, which is a chemical transport model. So that's kind of would calculate how the smoke will change chemically over time and how it will disperse spatially as with inputs about the weather. And so you can see with all these different parts in the model, there can be uncertainty coming from almost each part of this model. For example, there can be uncertainty about fire detection. So the satellite image, it may miss small fire, or if the image is obscured by cloud or even by smoke, then that fire hotspot may be missed. And then there's also uncertainty, certainly in the meteorological forecasts. We all know weather forecasts can be uncertain. So that will affect many parts of the output of this model. And then the model itself, some of the parameters that you need to set up to simulate that process can or has its own inherent uncertainty to begin with. So that's physical and deterministic model. And there's also another type of model called, we call it statistical models. It does not make assumption about the actual physical process, but just putting all the potential relevant data into a statistical or machine learning model. So the Canadian Optimized Statistical Smoke Exposure Model is an example of that type of model. So what it does is it uses historical data to train a model that can predict PM 2.5 with these relevant input data. So here in CanAwesome, it has data from satellites, it has data from meteorological models, and also, and with all these input predictive variables, it built a machine learning model called random forest model to try to predict and the PM 2.5 levels that measured at NAPS, so the regulatory, the gold standard air quality data that we have. So once that model or the historical relationship is established, then it can be applied to all the other areas that do not have regulatory monitors, and all the times when there's no data that's available. But with these input data, then you can still have the estimates of daily mean PM 2.5 concentrations from this model. So apparently, like statistical models, it relies on historical data. That's a main characteristics of these models, and that makes it one of the kind of vulnerable part is that if the historical data does not fit to the situation we have right now or the new situation, then it would not have very good performance. So just this, I got this table from Naman, and this is showing you that if you look at the last row of the table, it is a model that built with data from 2010 to 2022, and use that model to try to predict levels in 2023. And the performance was the worst among all the other times because it is 2023 is just unprecedented. And that's sort of a vulnerability of a statistical model that it really relies on historical data. And then AQHI is another type. It's not really kind of just air quality data, but it is air quality data plus health messages attached to it. And historically, AQHI is based on 3 pollutants, which makes it sometimes quite unsensitive to impact of wildfire smoke. And also it limits its spatial coverage because you will need to have measurements for all of these 3 pollutants in order to produce AQHI. And so that's why since 2017, we developed another algorithm called AQHI Plus that's trying to adapt AQHI to better reflect wildfire smoke. So right now, the AQHI that we see in reported out is the higher or the greater that's for of these 2 parallel algorithms. And that AQHI Plus algorithm is based on hourly PM 2.5 only. And we've also, at the BCCDC, we've developed some kind of more expanded message. That's the original AQHI health messages. They are focused mostly on outdoor activities. So we have developed some messages for reducing exposure at the different levels of AQHI. We've developed some recommendations for outdoor event planners, different actions that you may want to take under different circumstances, and also recommendations for schools. So I will not spend much time here, but you're welcome to look at the fact sheets on the BC CDC wildfire smoke website. And finally, air quality warning. Air quality in BC, air quality warnings are issued by Metro Vancouver for Lower Mainland and Ministry of Environment and Parks for the rest of the province. And these warnings are usually not issued based on a single threshold, but an overall assessment of current and forecasted situation and by meteorologists in these agencies. And they usually come with quite clear directives or advices for the public. However, they are definitely not a continuous type of air quality information. They are generally updated just on a daily basis, and they also intend to reflect regional impact, but not like very localized impacts. So if they would only issue these air quality warning if a majority of the forecast or that region or that forecast area is going to be or is currently being impacted by poor air quality. Okay, so goes into some thoughts and discussions that we may want to have. This sometimes can feel random as well. So the first thing that I in my mind is about the relationship between air quality warning that we just talked about. Is either yes or no type of air quality warning, and then the continuous monitoring air quality information that we have. And sometimes it will seem quite overwhelming to look at all these different types of information and think, can we just rely on air quality warning to guide our public? And that seems to be, a much simpler way. But my own short answer is no, because we can talk about this in comparison with hot weather or high temperature. And this graph, some of you might have seen it before, but it shows the relationship in red between temperature and the risk of mortality, and in blue for PM2.5, the effect of PM2.5. As you can see, the relation for temperature, there is very little risk for quite a broad range of temperature. But then when you reach a certain, a certain threshold, it's the risk increase exponentially. So this relationship makes a heat warning a very effective way to protect people from mortality, because once you hit that threshold, then really we need to take to take all the actions that we can take to try to reduce those exposure. But for air quality, it is very different. As the risk increase more steeply at low levels and plateau when it's above certain levels. So that means that we really need to monitor the air quality continuously, even at relatively low level, and do as much as we can to reduce our exposure as much as possible to that's the way that we should or we need to in order to have the greatest health benefits. And then this is also a random thought about the regulatory power of air quality warning. Historically, air quality warning has regulatory power, either to trigger emission reduction actions, for example, limit industrial emissions or wood stove use when air quality is poor. But in the context of wildfire smoke impacts, these regulatory power does not really apply to wildfire smoke. You can't really reduce from the source. So there seems to be. I'm just curious to know what folks are thinking about. Whether there's any role for air quality warning in terms of public health protection beyond these recommendations or health advices. Is there any role for it to play in terms of what outdoor events planner or organizers should do? Do they have a responsibility to provide alternative arrangement for attendees when there's a air quality warning? Or from the perspective of occupational health, is there any role for air quality warning to play? In terms of what kind of protections the employer needs to provide for employees? So this is really an open question or open topic for discussion. And then the other interesting things that I noticed is that who is producing and reporting these data? Conventionally, air quality data were mostly generated and reported by government agencies, which has a mandate and legally binded to provide accurate air quality data for regulatory purposes. There's also academia as another big contributor, especially in developing algorithms for, say, things like using satellite images or developing physical and statistical models. The quality of these academia generated data is usually assessed and made available mostly via peer review publications. It's a process for validating it or providing the transparency behind these data source. However, in recent years, I noticed that there's also more and more air quality data produced and distributed by the public and also by businesses. So yeah, as I prepare for this talk, I noticed that if you look at your phone, this right-hand side is the iPhone weather app, you will see the air quality is one of the things that you can look at in the default app, weather app on your iPhone. And it has, in the air quality, actually shows AQHI. And it's also, when you look at Google Map, you will also see AQHI shown on a map layer there. And I did a bit of research on what's behind these data, and it's actually not the official reported AQHI, but it was based on a model developed by a company. And so it is kind of a new way or a new kind of contributor of air quality data on the market. And it's very different from what we had historically. And these commercial air quality data, the obvious kind of benefit or advantage of these data is that it has really good. It is very convenient. It is just on your phone. It is and the most popular app, and it it is really easy for people to access it. However, what it is different is that it does not have it has less transparency in its algorithm, or we don't know much about how what's his performance. That doesn't mean that it's bad performance to begin with, because they also have the financial incentives to make a good product or to satisfy its clients. But it's just harder for us, for the public, to know exactly what the performance is, or try to externally validate them, because there's no obligation for them to disclose the model and the performance data to us. So that's that. And there's some tiny potential conflict of messaging that coming out from the source of data than the kind of the other conventional source of data that we've produced, like from the government, or there can be say 2 AQHI that's reported on your phone, and from the Metro Vancouver website, they may not always be the same. So that's some of the thoughts there. But at the same time, because of it is so convenient for all of these commercially available data, it also helps with some of the ideal scenarios that I have in mind for how people needs or how people should use air quality data. I think it would be ideal for people to check air quality as a routine, just as how they are checking the weather. And with such a routine, they would be able to actually do self-calibration, which means that you would be able to establish a personal exposure response plan. So just like checking the temperature forecast, for the same temperature, people can have different experience and response. Some people might need long sleeves at 20 degrees, while others still wear shorts. That can be similar in terms of air quality. Say an AQHI of 4 might not feel anything for some people, but for people that are more sensitive or more susceptible, they may already need to take actions to try to reduce their exposure. So having that routine to establish what your personal response to a certain level of air quality would be quite important, and that's a way of customizing the meaning of air quality information for more effective health protection. And we talk a lot about PM 2.5 or PM, and that there's a lot more other air pollutants in wildfire smoke that we may want to look at. And this is an example from Eric. And they're measuring some VOCs and other pollutants beyond PM, and trying to derive some kind of air pollutant profiles from from the wildfire smoke episodes in 2 different cities, and they already have some quite interesting results. And I think they're doing another campaign or summarizing data from another year, so that they will have some final results to show. But a short summary from me is that it seems to have wildfire smoke seems to have very distinct chemical profiles from the background, and it has specific way of these pollutants that there's some signatures that you can follow, and there's a lot more work that needs to be done on that front. And another rapidly growing field of research is to look at the long-term health effects of wildfire smoke and how to construct exposure metrics from air quality data to capture the different aspects of wildfire smoke. Long-term is an ongoing research question in this program of research led by Dr. Cleland and Sarah Henderson. And this work, I think it will help inform us what type of metric we should use to study and track long-term impacts, and also provide insights into what we should talk about long-term impacts when we're trying to communicate the public health guidance, because that's also one of the very routine question that we got from the public or from the media. What is the impact of long-term about wildfire smoke and how we should deal with it? So definitely something to look out for. And that's all I have for today, and I'm happy to answer any questions that you may have.
Thank you so much, Angela. And we've got 2 minutes until the end of the session here. So if somebody has something quick that they want to jump in with, I'll invite you to do that. And otherwise, we're going to ask you to use the react button to show Angela how much we appreciate her being here today, covering so much ground and being so responsive to our questions. And also, I would like to personally thank you for the many discussion points that you included at the end, because that you really, really responded to the brief there. So thank you so much. And I'm going to go ahead and press stop here on the recording.